All right. Well, hey, welcome to another lovely day here in Trig World. It's also a lovely day in Tahoe World. Holy cow, man. Anyway, so the plan today is to kind of just keep doing what we've been doing. We're going to keep looking at identities. We're actually going to develop a whole bunch of new ones today that are going to be really important for later on. But before I do that, I just want to ask you guys if there are any questions about homeworks or anything else we've talked about up to this point. Anything we'd like to chat about? Nope. Okay. Sounds good. So I'm going to go ahead and hop up to the whiteboard and I'll be right back with you. So I just had this thought as I was adjusting things on my phone so that you could hear me and I could hear you and all that. And you got to see that really lovely view of my forearm and all that. You guys must get really interesting things sometimes that come up on the screens from us unintentionally. So that's just a weird thought I had. All right, so today we're going to start developing more identities. And the first that we're going to build are what we call the sum and different angle identities. So these are exactly what they sound like. These are going to be identities that involve sums and differences of angles. All right, and so we're going to develop 6 of them, and we'll go ahead and just sort of make a list of what they're going to be, and we'll fill them in as we go. I'm actually going to put them over here, but we're looking at what happens when we take 2 angles and we add them together in sine. So we have sine of alpha plus beta. Remember alpha and beta, the little swimmy fish. That's the equivalent of A in the Greek alphabet. And then beta, the curvy B, that's their equivalent of B. So we tend to use those a lot as 2 arbitrary angles. Anyway, so we're going to have the sum of angles for sine, and we're also going to have the difference of angles for sine. So there'll be an identity for those. There's going to be similarly one for cosine that's alpha plus beta, and another one that's alpha minus beta. And then we'll also develop them for tangent. So we're going to develop these 6. We're going to build these 6. The first one's going to really come from just the geometry of the unit circle. But then after that, we're going to get all the rest using other identities we already have. The even and odd identities specifically, we'll use the cofunction identities, we'll use the quotient identities. So we'll see a lot of them along the way. So here's what I want you to take from this, because we're going to develop all these identities. And I know that you watching and me just talking, it can get really boring for you. And you're going to go, oh, whatever. Take this as a chance to practice all of the other identities. Help reinforce what all those other identities do as we're building these. Okay, so we're still going to use these. Like, there are going to be instances where we want to add angles or we want to subtract angles inside of our trig function, and we can't just distribute. It doesn't work that way. So we are going to use those identities, but use this derivation as a chance to refresh and practice all those other identities. Because the stronger those identities are in you, the faster you can recall them, the better off you're going to be in calculus. I promise. All right, so we're going to develop these 6. Now, if you're going to leave space to write what they're equal to, I just want you to know the 2 tangent ones are going to be fractions. So you'll need multiple lines for those. The other ones, sines and cosines, they're just one-liners. All right. So what we're going to do is we're actually going to go back to the unit circle. And I'm going to put two angles on here. I'm going to put alpha and beta on our unit circle. So let's make our unit circle. So this guy here. So there's a unit circle, and we need two angles, alpha and beta. So let's go with this angle right here. Let's make this our beta. And then I'll do another one, say in pink over here. And that's going to be our alpha. Okay, so those are just getting that. I just put two angles on there. They don't have to be those specific angles. Okay, so on the unit circle, just to remind you, because we're going to need to worry about this as well, these points where the terminal side intersect, remember that those give us the sines and the cosines. So this is going to be cosine beta, sine beta are the coordinates of that point. And the one that's over here for alpha, its coordinates are cosine of alpha, sine of alpha. Because that's how the unit circle works. All right, now, this is going to be the first thing that you're going to go, huh? Why are we doing this? But what I want to do is I want to find this length right here. I'm going to call it D. So how are we going to get that length? What do you guys remember? How do you find the distance between 2 points? Go ahead and type it in the chat box or yell it out. How do you get that distance? And remember, it's always okay. The answer of I don't remember is always fine. All right, well, how about this? So the distance formula, it was the square root of x2 minus x1 squared plus y2 minus y1 squared. I don't know if that just triggered anybody's memory, but if we use the distance formula on this, we're going to get that d is equal to the square root of, we need the difference in the x coordinates being squared. So cosine alpha minus cosine of beta squared. And then we add to that the difference in the y coordinates. So the same thing, but with sines. So we get sine alpha minus sine beta quantity squared. All right, so anyway, so there's your alpha and your beta, and we got this d for some unknown reason. Well, you'll understand in a second. So now what I want to look at is similar picture of the unit circle, but this time I'm just going to put on the angle alpha minus beta. So unit circle. Now on our picture up here, alpha minus beta is this distance right here, this rotation. Right? If we just take beta away from alpha, we're left with that. So what I want to do is I want to move that so that it's in standard position. So standard position means, of course, that the one angle is going to, or the initial side is on the positive x-axis, but then the other angle is going to be, or the other side, I should say, going to be there. So this is alpha minus beta. So in essence, all I did was I took this and I rotated it. Take this picture and rotate it so that the purple is now on the positive x and the pink is where the orange is. And so that means that that distance D is actually this same distance D right here. All right, so on this picture with alpha minus beta, connecting those 2 points is the same as connecting these 2 points. So I'm actually going to want to do the same thing. I'm going to want to get a distance on this picture, but let's think about what the coordinates of these points are. This point right here is going to be cosine of alpha minus beta, sine of alpha minus beta. And the coordinates of this other point, well, that's on this axis. It's a unit circle. That one we just know its point is 1, 0. All right, well, let's use that same distance formula for these 2 points. So we're going to get D equals the square root of the difference in the x's. So cosine of alpha minus beta minus 1 being squared, plus the difference in the y's, which is going to be sine of alpha minus beta minus 0. That quantity squared. So again, just using the distance formula, it's just 2 different points. But I know that those 2 distances have to be equal. So what I'm going to do is I'm just going to stick them together. I'm going to set one equal to the other, and we're going to do crap ton of algebra. Okay, we're going to do a whole bunch of algebra to simplify this thing down. So I'm going to erase my pictures. If you're like scrambling going, no, I need to remember, you can go back and watch the video. All right, but I need more space here. So what we're going to do is we're going to equate these 2 distances. Now, since they're both square roots, I can square both sides to get rid of those. So just to help us with the algebra, start the algebra, we're going to get cosine of alpha minus cosine of beta, that thing squared, plus sine of alpha minus sine of beta squared. That's going to equal, and I'm going to have to go all the way across the board now. That's going to equal cosine of alpha minus beta minus 1 squared plus sine of alpha minus beta minus 0 squared. All right, so this looks big, ugly, nasty, but it's actually not that bad once we do some algebra and simplify it. So I'm going to start by foiling these things out. So I'm going to get cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. So all of this came from squaring out cosine alpha minus cosine beta. Do the same thing for the next piece. So we're going to get sine squared alpha minus 2 sine alpha sine beta plus sine squared beta. So all of this was that piece. Okay, so now we'll FOIL this part out. We're going to get cosine squared alpha minus beta minus 2 cosine of alpha minus beta plus 1. So that was FOILing out this piece. And then the last one's actually not that bad, because when we subtract 0, nothing happens. And then we square sine, we get plus sine squared alpha minus beta. All right, so that was so long, I couldn't even do it all across the whiteboard. But this is where it gets nice. Let me highlight a couple things for you. For example, there's a cosine squared alpha and a sine squared alpha. What do I get when I add those together?
1.
You get 1.
All right, we get 1, and as Nicholas was doing this too, right? So that's going to give us 1. Sine squared plus cosine squared equals 1. Cool. Well, if you look really closely, there are some more of those. Here's a cosine squared beta plus a sine squared beta. That's also going to be 1. Right? Those are going to add together because that's a good old Pythagorean identity. And even better, if you look on the other side, we've got cosine squared alpha minus beta and a sine squared alpha minus beta. Those also are going to add up to 1. All right, so this is where I said it's going to get nicer real fast. So check out what we have. So we're going to get 1 plus 1, so that's 2, minus the 2 cosine alpha cosine beta, minus the 2 sine alpha sine beta. And then on the other side, well, those cosine squared and sine squared become a 1, plus another one is a 2, minus 2 cosine of alpha minus beta. So we did a whole bunch of algebra at the start, but then we made use of trig identities. We made use of that Pythagorean identity, and it definitely helps simplify it. All right, well, let's keep simplifying. I've got a 2 on each side, so those are going to cancel. I can divide everything else by -2. So I'm just going to divide everything by -2 to get rid of all those coefficients and whatnot. And what I'm left with, and I'm going to write it on, I'm going to flip sides just because I want to. But we're going to have cosine of alpha minus beta. That's going to equal cosine of alpha cosine of beta plus sine alpha sine beta. And go ahead and put a box around that, because there is our difference of angle identity for cosine. And this might feel a little weird, because you might go, well, if we're just doing a difference of angles, why can't we just do cosine of alpha minus cosine of beta? And the answer to that is because it doesn't work that way. These things, we can't distribute the trig functions over the addition and subtraction. They actually behave very differently. But there is a relationship. I mean, if we know what those two angles are, we just need to know their cosines and sines, and we can use this formula to get our answer. Okay, so it is what it is. I mean, you see why it has to be this way. We started with geometry, did a boatload of algebra with a sprinkle of trig. This is what it is. All right, so remember I told you we're going to get 6 of these things? Well, that's one of the 6. I love this. I love the fact that this just comes from, I'm going to say it, simple geometry. It was a really simple geometric picture. I had a circle with the 2, sides of my angle, and then all I did was I rotated it. Really simple geometry. But then with a lot of work behind it, gives us this nice little form. All right, so I want to give you rationale for why we do this, and where this can come in handy. So let's just dive right in with an example of where we would use this. All right. So for example, let's say I asked you to get me the cosine of 15 degrees. And I'm throwing you a bone here. We'll go to degrees for this first example because that'll probably be a little bit better. Although some of you may by this point are like, whoa, degrees, you never use degrees. Go to radians. The next one will be radians. But let's look at cosine of 15 degrees. Now, that's not on our chart. We don't have 15 degrees on there at all, right? We know 30, 45, 60, and all the other ones in the other quadrants and all that. Okay, but let's think about this. Can you make 15 degrees from the angles that we already know? Specifically with subtraction, and hopefully that's a pretty quick yeah. Because this is just the same as the cosine of, let's say, 45 minus 30. So what we're going to do is we're going to use this formula. So to translate here, alpha is our 45 degrees and beta is our 30 degrees. So we're just going to put those in their respective spots. So we're going to get cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 degrees times the sine of 30 degrees. And we know all these numbers. Those are all on our chart. We figured them out a long time ago now. So let's put them in. So we're going to get root 2 over 2 times, well, cosine of 30 degrees is root 3 over 2. And we can get a plus. Root 2 over 2 is the sine of 45 degrees. And the sine of 30 is 1/2. So it turns out that the cosine of 15 degrees, the exact value, is the square root of 6 plus the square root of 2 all over 4. All right, this is root 6 over 4 plus root 2 over 4, and I just combined them. But there you go. We just found the exact value of the cosine of 15 degrees. If you want a decimal approximation, yeah, you can go ahead and punch this into your calculator. I don't want decimal approximations here. Let's get the answer. But there's our cosine of 15 degrees. All right, well, cool. Now that we know the cosine of 15 degrees, we can add that to the list of angles that we know. If we can generate a sine of 15 degrees, then we'll be able to use this formula where either one of these is 15 degrees. And basically what this is going to allow is just to have more options in terms of exact values for angles. Historically, this was really important. Before the days of calculators and computers, this was huge. I know now you're probably going, yeah, but I've got like in my pocket a calculator that can tell me the cosine of 15 degrees. Yeah, good for you. Turns out we're still going to need these identities for other things. Okay, so even though I showed you this as an example of why we care, even though that may not be relevant anymore, the identity itself is still useful. All right, so there you go. There's the first of the 6. Now we're going to develop all the other ones. All the remaining 5, the other cosine and the 2 sine and tangent ones, using only identities. We don't have to go back to geometry whatsoever. We'll just go back to our identities. So the next one we're going to do is actually cosine of alpha plus beta. I think I've got enough space up here so I don't have to erase this one, but we'll see how this goes. All right, so here's what we're going to do. We're going to get cosine of alpha plus beta. Now, the way that we're going to do this is turn it into a subtraction problem. Because adding is the same thing as subtracting a negative. So cosine of alpha plus beta is actually the same as cosine of alpha minus negative beta. Now, the reason I did that is because we can now make use of the difference of angles identity, right? Alpha, well, that's still alpha. But now we're going to plug in negative beta where the beta goes. So this is going to look like cosine of alpha, cosine of negative beta, plus sine of alpha times sine of negative beta. So we're just replacing the alphas stay the same, but all the betas, we're now putting in a negative beta. Okay, so just remember that adding is subtracting negatives. We do that a lot in math. But now let's simplify these cosine and sine of negative betas. So which identities are going to help us simplify those? What group of identities deals with negatives inside? We don't have a really big list yet. We got reciprocal, quotient, cofunction, even odd, Pythagorean. So which of those are we using here?
We're using sum and difference.
We're building the sum and difference. But we're not going to use those for the negatives. Those are the even odd, the even and odd properties. Remember, for even functions, when you plug in a negative, you get the same thing as if you don't have a negative. For odd functions, when you plug in a negative, you can actually just pull it out front. And we know that every one of the trig functions is either even or odd. So we're going to make use of that. Cosine is an even function, which tells me that that cosine of negative beta is the same as cosine of positive beta. Sine, however, that's an odd function. So that tells me I need to bring that minus sign out front. Okay, so even odd properties, even odd identities. We use those anytime we're putting in a negative. Those are the ones that we're going to try to use. Okay, well, let's see what happens here then. We get cosine of alpha, cosine of beta. That minus sign, since I got a positive times a negative, that makes that negative. So we get sine alpha, sine beta, but it's being subtracted. All right, so we're going to go ahead and put a box around this because this is the identity for the sum of angles per cosine. So if we add two angles together, we have to put it into this formula. All right, so why is it that way? Well, because of the even and odd properties of sine and cosine. Okay, but check these out. If you compare these two, notice that they're almost identical. What's the only difference?
The top one has a negative sign.
Yeah, we've got this one's a positive, that one's a negative. So we're adding in one case and we're subtracting in the other case. Just like over here, we were adding angles and now we're subtracting angles. So the only difference between adding and subtracting is that in the formula, we change the sign. And in fact, the sign is opposite. Since we were adding cosines, it led to a subtraction. When we're subtracting angles, it led to an addition. All right, so just little tips to help you remember, because having to like rebuild it every time is a bit much. But if you can just remember the form of one of them, you got the form for the other. All right, cool. So we're a third of the way done with the sum and difference of angles identities. We've got the 2 for cosine. Yay. But now we got the other 4 we got to get. All right. So let's actually go to the top of the list and let's get the sine of alpha plus beta. Now, I'm going to need some more space, so I want to just sort of condense things down here. And what I'm going to do is I'm just down the bottom here. I'm going to put both of these identities together. And I'm going to write them like this. Since the left-hand sides, the only difference was one was a plus, the other was a minus. I'm going to put plus or minus. And then again, they both have the same form. So there's a cosine alpha, cosine beta, sine alpha, sine beta. But again, I need to allow those to be both the positive and the negative. But I'm not going to write plus or minus. I'm going to write minus plus. And I don't know if you've ever seen that before. We write the plus or minus all the time, like when we take a square root and things like that. But we never write minus plus. But the reason I'm writing it that way is so that if we're kind of reading across, the top operation here corresponds to the top operation over there, right? It's a plus with a minus, with the minus with the plus. So you'll often see it written like this. I'm not sure if the book ever condenses it down like this. But there are lots of places out there, if you're looking at other internet resources, you will see lots of times that they combine them. Because this is, again, the ultimate in laziness. Why write out 2 that are identical, with the exception of the sine, when I can just write out 1 and take care of the signs with those little symbols. All right. Anyway, so there are the 2 that we've developed for cosine. And I did that because when we go to the sine, when we develop the sine identity, we're going to need to make use of this as well. All right, so here we go. Next one. Let's look at the sine of alpha plus beta. So we're going to go ahead and try and build an identity that, looks sort of like this-ish, but for sine. Okay, so what we're going to do is we're going to relate this back to cosine. And there are a couple ways we can do that. We've already seen that sine and cosine are linked in lots of identities, right? If we just kind of go in the list of things that we did, they're not together in the reciprocal. They are together in the quotients. Tangent is equal to sine over cosine, and cotangent is cosine over sine. So they're part of that. The even odd, they're individual. They are part of the cofunction identities. And they're also part of the Pythagorean. Okay, so we really have 3 good choices for identities that involve sine and cosine. I'm not going to use the quotient because those require also knowing tangent or cotangent. And right now I don't know anything about those, so I'm going to skip on that. So that really leaves me 2 choices, either the Pythagorean or the cofunction. Now, it turns out for what we want to do, we're going to make use of the cofunction identity. So the cofunction identity says that the sine of alpha plus beta is the same as the cosine of pi over 2 minus alpha plus beta. Right? That was the whole point of the cofunction identities, is that in a right triangle, the sine of one is the cosine of the other. And that's what this is saying. The pi over 2 makes it so that it's a right triangle. Okay, so that was the cofunction identity. So cofunction identities are really good when you want to go from one function to its cofunction. So we're going to do it this way. Now I'm going to rewrite this using algebra as the cosine of pi over 2 minus alpha minus beta. And let me just really quickly show you where that came from. So with the subtraction, if I pass that subtraction through, I would get pi over 2 minus alpha minus beta, right? Distributing the minus sign. And then I just grouped it differently. I took the first two, I stuck them together, and then I subtracted beta. Okay, so just a little bit of an algebra trick. But now we're going to use the difference of angles identity for cosine. So that's going to give us cosine of pi over 2 minus alpha times cosine of beta. Cosine alpha, cosine beta. So it's the cosine of the two things. And then I'm going to have a plus, because it's the opposite sign, plus the sine of those two things. So sine of pi over 2 minus alpha, sine of beta. All right, so it's definitely starting to look more like the cosine identity. But I still have all this pi over 2 minus alpha stuff in there. Well, here's where I'm going to use the cofunction identities again. This guy, the cosine of pi over 2 minus alpha, that's the same as the sine of alpha. If I look at this other piece, sine of pi over 2 minus alpha, that's the same as the cosine of alpha. Again, directly using the cofunction identity. All right, well, there you go, my friends. There's the identity for the sum of angles in sine. Sine of alpha plus beta is actually equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. So much like these two, the cosine one, in order to do this, we're going to need to know the sine and cosine of the individual angles. However, they're put together in a different way. But again, that shouldn't shock you because it's a different function. Sine is not the same as cosine. So it is going to behave differently. All right, well, I want to give you a justification for this one too, before we move on. So how about we do this guy? Let's look at the sine of, let's go with 7 pi over 12. So again, that angle is not on our chart. We have nothing that looks at all like 12ths. But we actually can get this if we think of this as a sum of angles. And I'm just going to help you here by giving you the breakdown. This is actually the same as pi over 4 plus pi over 3. If you get a common denominator, it will be 12. If you build these up, you're going to get 3/12 plus 4/12, which gives us the 7/12 pi. Now, if you're looking at me going, dude, I never would have gotten that was pi over 4 plus pi over 3. A couple things. A, yeah, you eventually would have gotten it. B, yeah, I just know what I'm doing here because I've done it a million times. Don't hold yourself to my standard. But see, practice it. Just think about the different forms that you get when you add fourths and thirds and sixths, and same thing with subtraction, because those are going to be the ones that you tend to see on the homeworks. All right. You're going to get much better with adding fractions from this, by the way. All right, so let's use our identity then. So in the terms of alpha and beta, so we're going to put pi over 4 in for alpha and pi over 3 for beta. So we're going to get sine of pi over 4 times the cosine of pi over 3 plus the cosine of pi over 4 times the sine of pi over 3. All right, well, let's get those values. Those are on our chart. So this is root 2 over 2. Cosine of pi over 3 is 1/2. Cosine of pi over 4 is root 2 over 2. Sine of pi over 3 is root 3 over 2. And we end up with the square root of 2 plus the square root of 6 all over 4. And if that looks familiar, it should. That's actually what we found when we did the cosine of 15 degrees. So clearly, these angles are related to each other. Well, 15 degrees is actually pi over 12. And pi over 12 is going to be like the sine and cosines of those are going to be related to the cosine and sine of 7 pi over 12. So it just turns out that the sine of 7 pi over 12 is the same as the cosine of pi over 12. All right, but anyway, so there's how this works. And again, now we're opening up all kinds of angles that we can get, because now we can get sines and cosines of all these weird combinations, which then means we can use those as part of combinations, so on and so forth.
Do secant and cosecant work inversely with these two figures?
Okay, so if you wanted to do, say, since I've got sine right now, let's say cosecant. So you want cosecant of alpha plus beta, it's just going to be 1 over this. So
okay.
That's why we don't tend to develop those formulas, because like if I wanted to know the cosecant of 7 pi over 12, now I can just flip this over and it'll be 4 over root 6 plus root 2. So that reciprocal nature relationship still holds here. But notice that it's not take the reciprocal of each of these and add, it's add the whole thing up, then take its reciprocal. Does that make sense? Does that kind of answer your question?
Yes, thank you.
Yeah, okay, cool. All right, so there you go. There's sine of alpha plus beta. Well, sine of alpha minus beta is going to be done exactly the same way we did cosine, where we did the adding, the subtracting the negative kind of thing. So to build this guy, if we want to do sine of alpha minus beta, we're going to start by recognizing that it's the sine of alpha plus negative beta, because subtracting is the same as adding a negative. And now we use this identity. So we're going to get sine of alpha cosine of negative beta plus cosine of alpha sine of negative beta. We'll use the even odd properties again. So for cosine negative beta is the same as cosine of beta because it's even. The sine of negative beta, we pull that minus sign out front because it's odd. And so there's the identity for alpha minus beta.
How does that positive cosine turn into a negative cosine, the beta?
So hold on, you mean right here where it went from plus to minus?
Yes.
That wasn't, the cosine didn't change. It was the sine of negative beta is the same as negative sine of beta. And multiplying by a negative, I just brought the negative out. Does that make sense? So the odd property brought the negative in front of the sine, which then, because I'm multiplying, brings that negative out front. Think about, like, if you take 5 times -2, we just immediately write it as -10. So it's the same kind of idea. All right. So if you look at these two, I want you to notice that, yeah, they're identical form again, with the exception of the different plus or minus sign. And we actually saw that same pattern with the cosine, right? The only difference with the cosines was one was positive, one was negative. Same thing with the sines. The only difference is one is positive, one is negative. So if you know one of them, you know the other one. But this one's a little bit different because the plus goes with the plus and the minus goes with the minus, as opposed to with the cosine, we saw the adding of the angles led to subtraction. The difference of the angles led to addition. These two actually go together. But again, because they have the same form, you will often see them written together. It's the same kind of deal where we'll have alpha plus or minus beta. And for these, it's going to be sine alpha cosine beta plus or minus cosine alpha sine of beta. So we don't have to turn that plus or minus upside down this time, because the top goes with the top, plus goes with plus, minus goes with minus. All right, well, there you go. There are the sum and difference now for sum. So we're 2/3 of the way there. So I just want to kind of remind you what we've done so far. So we started with a little geometry, pretty simple geometry, that led to a ton of algebra and a little bit of trig that gave us one of the identities. We then made use of cofactor or cofunction identities, even and odd properties. So we've been able to use those to develop the others. All right, well, let's dig back into our bag of tricks, and let's use that to find tangent. So the last two we got to get, tangent of alpha plus beta and tangent of alpha minus beta. So let's start with plus. So we're going to do tangent of alpha plus beta. Well, in order to do this one, we need to get it back. We got to relate it back to the sine and the cosine. Ooh, I know what identity to use. How about we use the quotient identity? The fact that tangent is equal to sine over cosine. So we know that this is true. So how about we just take the identities for sine of alpha plus beta and cosine of alpha plus beta and fire those in here. So for the sine, we're going to get sine of alpha cosine of beta plus cosine of alpha sine of beta. Okay, so this is first one, but with the plus, it matches the plus. On the bottom, we're going to get cosine alpha cosine beta minus sine alpha sine beta. It's a minus because that's the opposite sign. But again, it's cosine times cosine and sine times sine. All right, so I guess we could put a box around this and say there's our identity, but this isn't the form that we usually see. We usually go to a different form. And to get this other form, we're going to multiply the top and bottom of this fraction by 1 over cosine alpha cosine beta. And right now you're probably like, what? Where did that come from? You'll see. You'll see why we want to multiply by this real quickly. So in essence, what we're doing is we're dividing each of these things, each of these 4 pieces by cosine alpha and cosine beta. So I'm going to write it out just that you can see what all is going to happen here. But we're going to get sine alpha cosine beta over cosine alpha cosine beta. And then the next one's going to be cosine alpha sine beta over cosine alpha cosine beta. And we'll do the same thing in the bottom. All right, so here are what those look like once we divided everything by cosine alpha and cosine beta. Remember last time when I was talking about miracle steps? This is sort of a miracle step. This was somebody eventually along the line said, ooh, hey, look what happens when I do it this way. All right, so it seemingly comes out of nowhere. It really came from just people messing around with this and seeing how they could simplify. But check out what happens now. Lots of stuff is going to cancel. Every cosine in here is going to cancel out. So let's look at what remains. We have sine alpha over cosine alpha. Well, that's better known as the tangent of alpha. The next piece, we have sine beta over cosine beta. Well, that's better known as the tangent of beta. If I come down to the bottom, everything canceled here. And so since that canceled from division, that means I have 1 left over. Right, it's not 0, it's 1. Anything divided by itself is equal to 1. And then the other part, if you kind of split it down the middle here, we have sine alpha over cosine alpha. That's tangent of alpha. And then sine beta and cosine beta. Oh, that's a tangent of beta. And so this is now what we're going to box, because this is sort of the standard form, what we normally see for the sum of angles for tangents. So if you're going to take the tangent of the sum of things, you have to add the individual tangents and then divide by 1 minus the product of the tangents. All right, well, again, this must be so. Now, think about what we used here. I mean, we used the sum and difference angles that we'd already developed, but we also made use of that quotient identity multiple times. We did it at the very beginning, and then we also did it with all these little subfractions that were still in there. It also just required a miracle step. All right, so we're close, right? We've only got 1 more to do, and that's what about when we have a difference of angles with tangents? Well, you've seen me do this now 2 times, so I know you know what we're going to do the 3rd time. When we want to go to tangent of alpha minus beta, we're going to think of this as the tangent of alpha plus negative beta. And we'll use this identity we just built. We'll just change all of the betas to negative beta. All right, so tangent. Is it even or odd? Remember, all the 6 trig functions are one or the other. So tangent, was it even or odd?
Even?
All right. So I got a guess of even from Robert.
I think it's odd.
All right. Nicholas says he thinks it's odd. Uh-oh. We're gonna have to have a fight, duke it out. How confident are you guys? I'm gonna go just to ask Robert, Nicholas, because they were the ones that said it. I'll tell you, Robert, you didn't.
Honestly, I just took a kind of a guess considering sine's odd, cosine even, tangent supposedly odd.
Okay. All right. So in terms of which one it is, tangent is also odd. The only even functions are cosine and secant. All the rest of them are odd. So tangent is odd, which means we're going to do exactly the same thing we did with sine. The minus signs have to come out front. So that's going to turn this into tangent of alpha minus tangent of beta divided by 1 plus tangent of alpha times tangent of beta. And it's a plus because that minus sign comes out front and a negative is a positive. So I'm sure it comes as zero surprise to you that it looks exactly the same, just with some different signs, right? In fact, both of the signs change. All right, well, that was common. And that's what we saw with all the rest of them. So we see that with tangent as well. All right, so we actually can write these together, and I'll go ahead and do it just like I did with the sine and cosine, just so you're familiar with it. If I want to, I could write tangent of alpha plus or minus beta. It's going to be a fraction. On top, there's a tangent of alpha and a tangent of beta. On the bottom, there's a 1. And then the product of tangent of alpha and tangent of beta. And in terms of the signs on top match, but we're inside the original tangent. And the signs on the bottom swap. So this one we have to use both the plus minus and the minus. All right, well, there you go. We just now developed the entirety of the sum and difference of angles identities. Now, it is just for sine, cosine, and tangent. But we don't worry about the other 3 because like we were talking about earlier, if you want the cotangent, do the tangent and then flip it over. You want the cosecant, do the sine and then flip it over, and so on and so forth. So we don't actually develop identities for those, but we can. We just don't. Because it's extra work that we don't need. All right, so I already showed you how we can use these to actually evaluate certain angles that are sums and differences of ones that we know. But I also want to show you how we use these to help with identities. Because we're primarily going to use these to help us do identities, solve equations, and then later on turn things into different forms, manipulate using the identities to turn into different forms to make life easier in the next math. So let's practice some of those. All right, so for example, let's do this guy. let's prove this identity. The cosine of x over the secant of 3x plus the sine of x over the cosecant of 3x, that equals cosine of 2x. So let's prove that identity. All right, so let's remember what we were talking about last time when we want to prove, establish, confirm, however we want to say it. Do this with identities. The process is pick one side and only one side, manipulate it using Tragan algebra until it looks like the other side. Okay, so we have to pick one side and go with it. And I suggested that you pick the uglier side. And hopefully we all can agree on an ugly side here. Right? In terms of our choices, I think the left is definitely uglier because it's got fractions and it's got secants, cosecants, and all kinds of grossness. All right, so I'm going to pick the left-hand side. So let's think about some things we can do with it. I gave you some general ideas, some things that can be helpful. The first was turn everything into sines and cosines. So if you've got the other functions, turn them into sines and cosines, and that can help. So that's something we could do here for sure, because we've got a secant and a cosecant. We could turn those into sine and cosine. Another suggestion I gave you was when you have fractions that are being added, to go ahead and combine them using a common denominator. So that could be another choice here, where we go, all right, let's take this and make it so that there's a common denominator of secant times cosecant. So those are probably the two best options right now. I'm going to suggest we get rid of the secant and the cosecant. Let's turn those into sine and cosine first. So secant is the reciprocal of cosine. So I'm going to rewrite that as 1 over cosine of 3x. And then similarly, the cosecant, that's the reciprocal of sine. So that's 1 over sine of 3x. Now, what that immediately leads me to do, since I'm dividing by a fraction, I'm going to flip them over and multiply. And when I do that, that's going to give me cosine of x times cosine of 3x plus sine of x times the sine of 3x. So there's a reason that I did this. At A, it got rid of my sine or secant and cosecant, but I saw at the same time, it's going to get rid of my fractions. Right? 1 over secant is the same as times cosine. 1 over cosecant is the same as times sine. So I got rid of my fractions. Now, if your first instinct would have been to add those fractions together, you will get similar forms, like you'll eventually get where we are now. It's just going to take more steps, actually. Okay, so here's where we are, which I wouldn't say really looks like cosine of 2x, but at least it's only sines and cosines now. All right, well, this is where the identities we just built come in. Notice this form. I've got cosine times cosine plus sine times sine. And if you look down, I actually still have this one on our list. I haven't erased it yet. that looks a lot like this one, right? Cosine times cosine, sine times sine. So I'm going to use this to put this in together to one cosine. To translate it here, we're going to have alpha is equal to x and beta is equal to 3x. That's the form we've got here. So putting that together turns this into cosine of x minus 3x. So I wanted to show you, I like showing this identity specifically because it made us use this identity backwards. And a lot of the time we forget that identities both go, they go both ways. So we always tend to think left to right because we read left to right. We do math left to right. So it's always left to right, left to right, left to right. With identities, they can go right to left. And sometimes that's the trick you need to make it so that you can actually solve what you need to solve. All right, well, let's see what this does then. Cosine of x minus 3x. Well, if I subtract those, I get cosine of negative 2x. So we're almost there. And I actually know that this is the same as the cosine of 2x. And what's the justification there? Why does that minus sign go away?
Cosine has to be positive.
Well, cosine doesn't have to be positive. I mean, I want it to be positive.
It's like the even rule.
Yeah, not like, it's exactly the even property, right? I'm putting in a negative into cosine. The even property of cosine says, well, you don't have, you can ignore that negative. It's the same as the positive. So whenever you get a minus sign in there, I want you to think, minus sign in there, think even odd, even odd, even odd, even odd. All right, that should be a trigger. As soon as you see that negative in there, start thinking, ooh, what does even odd tell me? Because that's frequently, very frequently, the trick to dealing with it. All right, well, there you go. We just proved that identity. And in the real world, or where this could come up, is if you had some sort of an expression where this got built. Don't ask me to think of something off the top of my head where you would get an equation like this. But let's say you had that expression. I most definitely would rather just turn it into a cosine of 2x. It's less to write, it's easier to manage. It's going to be easier to solve if this was an equation. It's going to be easier to simplify with other things, right? And that's the whole point. The whole point of having all of these identities is so that we can manipulate the form into something that's nicer. And I think students tend to not think about that when they're doing these homeworks. Like, I don't know if you guys have started these homeworks, but these homeworks are kind of dry. They get kind of boring unless you're like me, and then you have other issues. But it's kind of just like, oh, good Lord, it's another identity. I want you to always keep in mind why I'm making you do this, and make is kind of strong because you're your own person. You can choose to do it or not. But the reason that I'm suggesting that you do this is to practice it so that later, when it does pop up, it makes your life easier. I can't tell you how many times, even in the real world, I manipulate the hell out of things algebraically using trig and stuff like that. But it's because I'm really comfortable with them that I see it and I see the opportunity. So this is how you get comfortable. Anyway, I'm starting to preach. I don't want to preach. Do the opposite. You'll get better. I promise. It'll suck at first. Absolutely. It will get less sucky as you go. All right. And then eventually it'll turn into hopefully, it'll turn into, this stuff's not that bad. And maybe I'll even get a, ooh, this is kind of fun from one of you. I like setting the bar high. We'll see. Okay, so there is a whole nother class of identities we now have for sum and difference of angles. And again, they're used for when you've got a sum or difference of angles inside of a trig function. Just remember that they do go the other way as well. All right. So I'm actually going to move into the next set. The next set is small. There are only 3 of them. And these are what are called the double angle identities. And I bet you can tell me what they look like, at least what we start with, right? Think about what double angle means. When we double something, we multiply by 2. And so the double angle identities, they're going to look like this. Sine of 2 theta equals cosine of 2 theta equals, and tangent of 2 theta equals. All right, it's exactly what they sound like. So these are going to be the identities that we use when we double an angle. Again, I know the instinct, what you're going to want to do is just pull the 2 out front and go, oh, sine of 2 theta is the same as 2 times the sine of theta. Don't do that. Don't do that. Because it's definitely not true. I mean, we have angles already on our chart where you know that's not true. Like, think about 45 degrees and 90 degrees. 90 degrees is double 45, right? The sine of 45 is root 2 over 2. The sine of 90 is 1. That's not even close to double root 2 over 2. And you see the same thing with the cosines. Cosine of root 2 over of 45 is root 2 over 2. Cosine of 90 is 0. Well, that's definitely not double. Right? Tangent, even worse. Tangent of 45 degrees is 1. Tangent of 90 degrees doesn't even exist. All right, so that algebra definitely doesn't hold, which means there has to be some other relationship, and that's what these identities are going to do for us. These are fast. These are fast, and these are easy if we use what we just developed. All right, check this out. We'll just start at the top. Let's go with sine of theta, or sine of 2 theta. So sine of 2 theta, think about what doubling means. Multiplying by 2 means we're just taking the same angle and we're adding it to itself. So doubling is the same as a sum of angles. So we can actually use the sum of angles identity for sine. So if we go back and look at what we derived just a little bit ago, this is going to equal the sine of the first one times the cosine of the second, plus the cosine of the first times the sine of the second. So when you go back to that formula, just realize that both alpha and beta are the same angle. I'm calling it theta here. They're identical. All right, so we've got sine of theta times cosine of theta, another sine of theta times cosine of theta, which means I can combine those. And we get 2 sine theta cosine theta. And there it is. There's the double angle identity for sine. So it's kind of trippy. I mean, it's still got the 2 in it. So it's like, oh, I am doubling the cosine, or sorry, the sine, but you're also multiplying by the cosine. It's just a little bit of magic, that has to be played. Because the geometry says so. Like all of this comes back to the geometry of the circle. It has to be this way. All right, well, there you go. There was sine of 2 theta. So guess what we're going to do to get cosine of 2 theta? Same thing. The tangent of 2 theta. Same thing. We're going to go to their respective ones. All right, so here you go. Here's the next one. Cosine of 2 theta. It's the same as cosine of theta plus theta. So we're going to go to that sum of angles identity, and we're going to change all of the angles to thetas. So it was the cosine of the first times the cosine of the second minus, at the opposite sign, the sine of the first times the sine of the second. So that gives us cosine squared minus sine squared. All right. There it is. There's the double angle identity for cosine. I need to warn you about this one. Because if you look at this one, this looks an awful lot like another one. What other identity have we seen that has something that looks a lot like this?
Pythagorean.
Yeah, think back to that Pythagorean. That was sine squared plus cosine squared equals 1. This looks almost the same, except there's a subtraction. Be very careful with this, because many times, and I only bring this, I've been teaching trig for a couple of decades, and there are some things that happen regularly with students, and this is one of them. They see the cosine squared and the sine squared, and they get so excited that they immediately go equals 1. But it doesn't equal 1 because it was subtraction instead of addition. So just watch out for that. Please don't fall. All right, well, there you go. There's cosine of 2 theta. So if we want to do the double angle identity for tangent, same story. There's going to be the tangent of theta plus theta. All right, so that form, it was the tangent of the first one plus the tangent of the second. So we'll just put thetas in for both. And then on the bottom was 1 minus the tangent of the first times the tangent of the second. And so we can combine this and simplify it a bit. We get 2 tangent of theta over 1 minus tangent squared. And so that's what's going to go into that third line. Okay? So 2 tangent theta over 1 minus tangent squared. And just like that, we got the double angle identity. They're just the sum and difference. I mean, they're the sum of angles identities. Just where we're adding the same angles together. But they come up enough that we like to have them as a separate form. All right, so, and I'll tell you specifically, the first one, oh my gosh, this first one, I use this all the time in calculus. All. It's probably my second biggest use other than after the Pythagorean. Right. So other than that, that one tends to be a big one. So you'll get used to seeing that, I promise. The other ones, not as much. But it turns out that the cosine, double angle cosine, we're going to use that next time to develop a couple of more identities. But I also want to point one other thing out. The cosine of 2 theta, there are a couple other forms that we use for it. So there really are 3 good forms. The first one is what I've got written. So cosine of 2 theta equals cosine squared minus sine squared. But I'm going to give you two other forms. And those other forms come from the Pythagorean identity. So remember that sine squared plus cosine squared is equal to 1. So I can actually solve this for either one of them. So for example, I could write sine squared equals 1 minus cosine squared. Or I could write cosine squared equals 1 minus sine squared. And what I can do is I can actually substitute these in for the respective pieces in the identity. So like if I take care of the sine squared, for example, if I take the cosine squared minus sine squared, I can write that as cosine squared minus 1 minus cosine squared. And if I distribute the minus sign and group them together, I get 2 cosine squared minus 1. So that's an alternative form to the double angle for cosine. If I do the same thing, but I replace the sine, or sorry, the cosine piece, I would have 1 minus sine squared minus sine squared. And again, if I just group like terms, this one looks like 1 minus 2 sine squared. So it's totally allowed to do this. I mean, it's totally fine. But I know at this point, I'm often asked, why? Are we just doing this to do math? No. Yes and no. I mean, it's good to practice with the other identities and put them in. You're kind of like I was talking about earlier. Use today all this derivation as practicing old things. So yes, some of it is just to do it, but it actually has incredible use. Some you'll see next time when we create these ones that are called the power reduction identities, and also in the half angle identities. But even more to the point, look at what you need to know if you want to find the cosine of 2 theta. With the first form, you need to know both sine and cosine. So whatever that theta is, you actually need to know both sine and cosine. For the other two, you don't need to know both. Right? The second one, you only need cosine. And for the last form, you only need sine. So having these other forms is actually really useful depending upon what information you have. Right? If all you know is the cosine of that angle, just jump straight to that middle one. If all you know is the sine, yeah, use the last one. If you know both of them, then use any of the three. So functionally, like actually like doing stuff, these other two forms tend to be even more useful because they're saving you step. Like, then you don't have to use the Pythagorean identity anymore. You already did it when you created it. All right. Okay, so I know that today I just threw a crap ton of identities at you. It's actually not that many. The sum and difference, there are only 6 of them, and they all look alike. So it's really there's only 3. And then I give you the double angles, which are really just the sum of angles. So it feels like a lot. And we did a lot of algebra and we did a lot of trig. So I know that probably right now your brain is swimming in letters and everything. So we're going to go ahead and call it today. We're going to stop here. But what I want you to do for Monday, all right, over these next 5 days, play with these identities, look back over the derivation, follow all the different steps, practice doing them yourself. See if you can derive one of them from the other, but practice, use them. The worst thing you could do, the absolute worst thing you could do right now is as soon as you hop off Zoom here, you just sort of like forget about trig and you don't think about it again until Monday you turn Zoom back on. If you do that, you are not going to learn identities, and identities are going to suck for the forever. Okay, this is just reality. If you want to get comfortable with these, if you want to get better at them, just look at them every once in a while. Keep them fresh in your brain. Okay, that'll definitely help. Other than that, I think the only thing I would want to remind you about is that homework is going to be coming up due on Monday, but that's forever ago. Oh yeah, one other thing that I'm going to do, we are on tap for an exam on Thursday. Because we bumped the other one, I'm going to bump this one as well. So Thursday, I meant Wednesday. So I'm going to put out a Canvas message, but I'm going to swap quiz and exam again. So we'll move exam 2 to the following week. But I'll put it all down in a Canvas message so you got it. I'll change the due dates in Canvas so that they're all there. But just so you know, we're not going to do our exam next week. But the following. Okay, well, I think that's all I've got to share, unless you guys have anything, any other questions or comments before we call this. All right, I'm not hearing any and I'm not seeing any, so I'm going to wish you all an awesome weekend, and I will see you all on Monday.
Thank you.
You're welcome, guys.
Thanks, Bruce.